Okay, picking up where we left off with talking about how we read the standard reduction potential chart. So now let's look at these two examples of galvanic cells. We know that they're galvanic cells because they've got a voltmeter and we don't have any kind of electrical power source pushing those. Same thing, this is basically how we would draw them. The first one looks kind of like what we would draw to look like the animated version. Something that I want you to make note of is this right here, and that is the anions from the salt. That's talking about the salt bridge, are going to move to the anode, while the cations are going to move to the cathode. And that's because, of course, that cathode is having electrons deposited on it, and so it's going to interact with those electrons, and then in this case the copper 2+ is going to accept those 2 electrons and deposit copper metal onto the cathode itself. Okay, so now let's work a quick problem. We're going to be using those reduction potentials that we just talked about in the last video lesson, so you may have to flip back a little bit. Let's see if I can get that whole, nope, I can't get the whole thing on there. So this says consider this galvanic cell. Let's just get used to this right now. Galvanic means thermodynamically favored, so some things that we can see by the word galvanic is that delta G is going to be positive, and that our E naught for the cell also needs to be positive because it is a thermodynamically favored electrochemical cell. So we have aluminum 3+ going to aluminum, so they're telling us right there what is being reduced, right? Because it's gaining 3 electrons. So that's going to be reduced, so that helps. Sometimes we have to decide for ourselves based on those values. And then, of course, magnesium is losing electrons, so it's being oxidized. So what we're going to do is we're going to say the aluminum is Al3+. We're going to add 3 electrons to that to go to aluminum. We look up that particular value, and that is going to be reduced, so we'll be able to use it straight off of that table, which is a negative 1.66 volts. So E cell for that one is negative 1.66 volts. And then magnesium is going from the 2+. And we're going to show that it, oops, I did that backwards, I'm sorry. I knew that didn't look right. Magnesium is going to go to magnesium 2+, and then it lost 2 electrons. So when we look up that value, if we look it up straight off the table for magnesium, it's going to be as a reduction, okay? And so it's going to say a negative 2.37, but because we reversed it, we have to change the sign. So we reversed, so we're going to say E cell is positive 2.37. You don't have to write the positive, but I just do it to know that I changed the sign so it reminds me. So now my E for the cell, for the entire thing, is going to just be adding those together. So it's going to be 0.71 volts. So what that means is in that electrochemical cell, or that galvanic cell, I would be able to produce 0.71 volts of electric current. Now it wanted to know the balanced cell reaction, and I'm going to change colors and remind you that in order to balance that, we have to have the same number of electrons. So we're going to multiply this by 3, this by 2, so that my final equation balance would be 2 aluminum ions plus 3 magnesium is going to produce 2 aluminum, and I'm going to go ahead and put the solid so we know that those were solids, plus the magnesium 2+, which would be aqueous. So let's go put all that on there so we know aqueous, solid aqueous. Okay? And the electrons would cancel each other out. Again, I'm going to stress that in this, we multiply to get the number of electrons. We reverse signs, but on E cell, we do not multiply the E cell by those integers. Okay? All right, let's see what B says. B says a galvanic cell is based on the reaction. You'll need a more complete table of reduction potential, so I'll give them to you on this one. We've got permanganate, hydrogen, ion, chlorate going to perchlorate, manganese, and manganese ion, and water. Okay, so I will be giving you those values for that. Okay, so we're going to do the manganese, MnO4, going to Mn2 plus. Well, we just did that a while ago in the previous slide, so I'm just going to give it to you. That gives you 4 water, and then it gives you 8 hydrogen, right? And then to be able to balance that, we have plus 5 electrons for that one. And then I will give you that that one is being reduced, so that E value is, I don't think it's on the table, I'm not sure, it's 1.51 volts. For the chlorate, going to perchlorate, it's going to need 1 electron. And then that value from a more extensive table is negative 1.19 volt. So when you add those up, you get 0.32 volts. And then, of course, in order to get that one to work out, we got to do 5 times 5. And then, so we end up with 8 hydrogen plus the permanganate plus 5 chlorates is going to produce Mn2 plus 4H2O plus 5 perchlorates. Okay? All right. Moving on, the next one says calculate the cell voltage for the galvanic cell that would utilize a silver metal and involve iron 2 ion and iron 3 ion. And then the next thing it wants you to do is draw the galvanic cell for the reaction and label it completely. Okay? So we're going to finish this, and then we're going to stop this video and then move on to cell potential. Okay, so this will be the last part of this video. All right, so what do we want to do first? Do we want to calculate the cell voltage, or do we want to draw? It doesn't really matter, except that you do have to know the voltage to be able to draw that in the voltmeter. So let's figure out, if we look up the values, we are going to have to do, if we look up the values, silver to be reduced, so let's just do that. Silver, whoops. The reduction potential for silver is Ag plus going to Ag, and that E value is 0.8 volts. To do iron 3 plus an electron going to iron 2, if we look up that one, we get 0.77 volts. And remember, I told you whatever is the most positive gets to be reduced, and the other one has to be oxidized. Another thing is that we know this is a galvanic cell, so that means the overall E cell has got to be positive. So we're going to reverse whatever is going to make this be positive for us. So we're going to say we are not going to keep it this way. We're going to mark that out, and we're going to flip it. And so we're going to say Fe2 plus is going to be oxidized. And then we're going to say that that becomes a negative 0.77. So overall, luckily everything's 1 electron, so that makes this easy to balance. So our E cell is 0.03 volts. And then our final balanced equation is going to be Ag plus, and our net ionic at that, Fe2 plus, going to Ag plus Fe3 plus. So now that we know how to do that, let's draw our cell. Okay, so we're going to start out drawing our little beakers. Okay, we're going to go ahead and draw that salt bridge in there. Don't forget the salt bridge, because if you do, that will be points off. So I apologize in advance. This is going to be messy. Okay. Then we need to draw some electrodes. between the electrodes, because this is galvanic, we want to draw how many volts we're going to be able to pull. And then we're going to connect them with our wires. We want to show the flow of electrons going this way. So always show your flow of electrons. It doesn't really matter whether you draw, you could flip this and do anode to cathode. I just out of habit always go anode over here because it's in alphabetical, but you don't have to. You could do the cathode first, but then you make sure you show the flow of electrons. The cathode is positive, the anode is negative. Okay? Because we're doing iron, and we're going from a +2 to a +3, we would not do a iron electrode. You're very rarely going to ever do an iron electron. For one thing, they rust. So we're going to use a platinum, and then this, of course, would be silver. And then we've got that labeled. In this solution, we would have Fe2 plus and Fe3 plus floating around because you're going to be losing electrons. And then over here, we would have the Ag plus. And then, of course, what did we say a while ago? We said that the anions from the salt go to the anode. So we would have our, let's draw some liquid in there. So we're also going to have some nitrates over here. And then over here, we're going to have the Ag plus. There would also be some silver in there, but it's not going to worry about it. Okay? Now, most likely we'd have some nitrates in here too, because we would be using probably AgNO3 to get it, and we would probably be doing Fe, both of the FeNO3s. Those would probably be in there. You don't have to write that. I'm just showing you that those would also be in there because these are aqueous solutions. Okay? So that is how you would draw all that. Now, I wanted to show you a shortcut. Sometimes you might see it on an old worksheet or whatever, but you draw the cell exactly what you see. So you draw the anode, and then you draw a line saying that the anode is with the Fe2 plus. Then we signify the salt bridge by a double line, and then the next thing would be the Ag plus, and then the line, and then the cathode. That's just kind of a shortcut. You don't see it that much anymore, but you might occasionally on an old worksheet, and I didn't want you to be lost or dazed or confused. So we're going to go ahead and stop that video there, because the next set of videos is going to have some calculations. Okay?